Good morning, doctor. We are Group 5 from Section 1. Today, we are present the flash separation design, which is acetone and chloroform. We have three group members. The first is Ko Yong Hao, the second one is Anzawei, and the third one is Mok Suni. Good morning, doctor. My name is Anzawei. Firstly, I will talk about the introduction of the flash separation. The flash separation is a key unit operation in chemical engineering and process industry, particularly in the field of petrochemical, natural gas processing, and refinery operation. It is a technique using to separate a liquid mixture into its vapor and liquid components based on their different volatility. Flash separation operates on the principle of partial vaporization. For example, when acetone chloroform mixture is subject to a sudden reduction in pressure or an increase in temperature, a portion of the liquid flash into vapor. The resulting vapor phase is richer in the more volatile component, while the remaining liquid phase is richer in the less volatile component. This separation occurs because different components of the mixture have different vapor pressure at the given temperature. Nextly, I will talk about the objective for a flash separation process. Firstly, the first objective is achieve effective phase separation. The flash separation process will separate the mixture into vapor and liquid phase. The second objective is the purity of a product. We should ensure that each phase has the target composition. And third objective is to maximize the recovery. The flash separation process will optimize the recovery of acetone in the vapor phase and the chloroform in the liquid phase. The fourth and fifth is the energy efficiency and process efficiency. We ensure that the process is energy efficiency. And the last objective is the safety and environmental compliance. For a flash separation process, operate continuously and safely adhering to environmental standard. Lastly, I will talk about the process of the condition. For our group 5, our binary mixture is the acetone and the chloroform. The temperature we choosing 60 degrees Celsius is because 60 degrees Celsius is a temperature that can be easily maintained and controlled in the industry setting. It does not need requires high temperature equipment which can be expensive and challenging to maintain. The pressure we choose the 180 or 106 kilopascal, and our overall composition will take 50% of acetone and 50 more percent of chloroform.
Next, let's move to the calculation part. Firstly, we need to calculate the saturation pressure for the each species. By using table B to a 20 question, we get that the saturation pressure of acetone is 115.1557 kilopascal, and for the saturation pressure of chloroform is 97.7525 kilopascal. Next, calculation due and back pressure. As our process condition is 50 mole percent acetone and 50 mole percent chloroform, to calculate back pressure, we use the formula of 0.5 times saturation pressure of acetone plus 0.5 times saturation pressure of chloroform. For back pressure, we got 106.45 kilopascal, and for the due pressure, we got 105.74 kilopascal.
Next, moving on to the flash calculations. First, we will start by obtaining the k-value coefficients. First, k1 would be obtained by dividing p1 set over p, and for k2 will be p2 set over p. Then we will get k1 equals to 1.0864 for acetone, and k2 is equals to 0.9229 for chloroform. Then, by plugging in the values into the trial and error, the v values will be found to be 0.6980 to obtain a summation of Ziki divided by 1 plus V Ki minus 1 of 1. On to the next part, where we find the molar fraction of the vapor and liquid phases. The V will be the result we have obtained from the previous trial and error, which is 0.6980, and for L will be 1 minus V, which will be equal to 0.3020. Then, to obtain the composition of vapor and liquid phases, we use the formula Y1 is equals to Z1 K1 divided by 1 plus V multiplied by K1 minus 1. And the same goes for Y2, by substituting Z2 and K2. To obtain Y1 is equals to 0.5123 and Y2 is equals to 0.4877. For X1 and X2, the equations used are X1 is equal to Y1 divided by K1, and the same goes for X2 by using Y2 and K2. X1 will be equal to 0.4716 and X2 will be 0.5284.
In conclusion, when designing a flash separator to separate acetone and chloroform and calculating the moles of liquid and vapor, along with liquid phase and vapor phase mole fractions, it is important to consider the thermodynamic properties of the system. This involves utilizing vapor-liquid equilibrium data to determine the compositions of both phases at equilibrium. By using this data to calculate the moles of acetone and chloroform in the liquid and vapor phase, as well as the liquid phase and vapor phase mole fractions, it is important to optimize the design and operating conditions of the flash separator to achieve the desired degree of separation. Furthermore, considering the system's energy implication and safety aspect is essential, necessitating the implementation of suitable measures for ensuring safe and efficient operation of the flash separator.